My name's Kevin Wolf. I am the co-founder and uh, the CEO of Wind Harvest. I've been working with the company for quite a while. I'm excited to be here at the stage where we're finally able to bring this turbine through certification and into sales, which is quite exciting. And I have a slideshow to show you. So I think I will just jump right in and share my screen with you and start with that. Um, so this, excuse me, here we go. So I'm going to turn this into the view as slideshow, and here we go. That's a picture of the turbines might look like in a wind farm. This is a real wind farm up in the UK area, and we added a properly sized turbines through that wind farm. And this basically, in this picture, pretty much doubles the energy output of the wind farm, and that is the mission. There is this turbulent wind near the ground, and these tall turbines in these wind farms cannot make use of this energy. They need to be up in smooth laminar flow, high above the ground, and that leaves this layer in the world's best wind farms without a technology to use it. And that has driven the company since its beginning, how to create the first technology that can make use of it. And we are just about well, we're there. We just need to now roll it out. So the agenda we're going to talk about the history of vertical axis turbines, key challenges that have stopped coming into the market, and some of the other turbines or machines that can make use of this turbulent wind. We're going to talk about how we resolve these problems, and then we're going to go through some of the competition. And I'm going to give a little bit of kind of what do we call that? Logistics for this today. If you have any questions, we're not going to be able to answer them in this call for a number of reasons, but we want you to add those questions to the Start Engine discussion page, and I will answer them in more detail there. So I know I'm not going to cover everything that could be covered in this subject matter. So I'm appreciative of your messages in the Start Engine discussion page. Jake, who's also on this call, is putting up some links in the chat so you can follow up and find some references on some of the things we are doing. So I'll start right off. So some of the very first wind turbines were Darius vertical axis wind turbines. This is a Frenchman named, I forget his first name. He's created this, it's called an egg beater type turbine. So the big breakthrough in Darius turbines was when Sandia National Lab started developing these vertical axis turbines. And here on this picture on the right is a picture of the turbines that Sandia National Lab, it's the largest turbine they made. It's called the 34-meter turbine. It was made in the 1980s. And the reason why I love this picture so much is that that person on the left, that young man, is Dr. David Malcolm. He was recruited to help solve this problem of flow wind turbines, which I'll tell you about in a second. But Darius turbines had a lot of admirers, and there's a lot of money invested in them. This turbines on the left, they have these steel instead of cables. If you want to look on the right, that 34-meter one is the center of that rotor is held up by cables to make it stationary. The ones on the left, they're held up by these, what you might call little steel structures on tripods. And that, one of the benefits of having it curved at the top is you could have these tripods not have to swoop out so far if it was an H-type turbine, like Wind Harvest has an H-type turbine, which I'll go into in a minute. But vertical axis turbines, Darius turbines had a number of difficult problems. So I'm going to show you this flow wind turbine. So Flow Wind took the Sandia National Labs public domain information about their Darius type turbines. They had some basic engineering tools from Sandia National Labs, but this was early. They were racing the deadlines in the United States that ended renewable energy tax credits. President Reagan came to office and he ended the tax credits, and then Jerry Brown ended it. It was stopped being governor of California in 1982, and then the California tax credits ended, and that made Flowwind rush into putting in 500 vertical axis turbines or Darius type turbines in mostly in the Tehachapi Pass in near the Mojave Desert in California, down up in the Altamont Pass, and in various places around the United States. And they did well for the first few years. Now this, I'm going to show you some things about these turbines. This Flowwind has 2 blades. They came up with a later version that had 3 blades that was taller. And when I talk about some of the problems of these Flowwind turbines, is a 2-bladed turbine, both in horizontal axis turbines and almost any vertical turbines, has a number of problems that 3-bladed turbines resolve. It's interesting that both horizontal axis turbines, the propeller type turbines, all pretty much are standard in 3 blades. And vertical axis turbines have moved in that same direction. The modeling and everything shows that 2-bladed turbines have significant problems. So that's one strike against the Flowwind turbine. But the other strike they had, the biggest strike, was these turbines operate and revolve millions of times a year. And I'm going to show you my little arrow here. This is the strut from the center mast to the blade. There are 4 of these struts. That connecting point here had serious problems. There are various forces. There's a flapwise bending force that pulls the blade outward, and then there's this force that pushes it forward. And that forward push force really did a number on this arm connection. And it's worsened because it's a 2-bladed turbine. There is a very good story that's going to be in the chat from a guy named Paul Gipe. He is just a wonderful resource on wind turbines, his WindWorks page. He has a special thing about the Flowwind turbines, and there is in there some communication by Dr. David Malcolm about his experience in working to help Flowwind solve this problem. So now they're 5 years in, and their blade arm starts to show cracks and starts to break. So David Malcolm and the consulting firm he was involved in came in, and they figured out, oh boy, they're going to have to put a plate on every one of those arms, blades in 2 places, so 4 plates per turbine. They're going to have to take those arms off, epoxy on the plate under very specific conditions, and then put the blade back up. And by the time they figure that out, almost every turbine either had already fractures in their blade arm connections or were going to fracture. And by 1994 or so, 2000 or so, you can read it in the story from Paul, they were all gone. They had all broken. And so that was the end of the Flowwind turbine. And because it was early, it caused people to have doubts about vertical axis turbines in general. How can you resolve these problems of these blade arms breaking and this rotation of millions of times a year? So what we have, that brings us to our turbines. We have gone through the technology readiness level processes, and that is, I'm going to see what happened. Oh, there we go. I knew I had this one, another slide. Good. So this picture on the top right is Bob Thomas in front of 3 Model 530G turbines down in Palm Springs. The turbine on the left is one of the very first turbines they made. The issue that they had, that vertical axis turbines have, is it's hard to predict where harmonic resonance shows up. So the solution to that was to create a structure that holds the center of the mast steady. And then you turn it on and you figure out where harmonic resonance is, and you make sure that your operation does not occur in that harmonic resonance profile. So, for example, most of our turbines around 50 RPMs was safe, 40 RPMs was a danger. You moved up to 50 RPMs. You set it as a single speed at 50, and voila, it was safe. So the early company, Wind Harvest Company, went through numerous different variations of this, including a project that was going to be done in Wales that we can tell you about. Those are the turbines in the center of the bottom at Prince Charles's property. For lots of reasons, it never actually went commercial, but it's a good story. That's me on the bottom right in front of these turbines down in Palm Springs. So a couple things you'll notice, these turbines in Palm Springs, we don't have these stators on the outside of the turbines, these pillars that you see on the far left turbine. What we have is guy wires, kind of like the Darius flow wind turbines that keep the center mass steady. You'll see there's a lot of blades and a lot of arms, and that was because Bob was concerned that without a blade every 30 degrees, it would not create enough continuous energy and you'd have problems with power quality. Well, we figured out through a number of experiments with Bob's leadership in the early days that we could make a three-bladed turbine. So this is our first three-bladed turbine on the left. It was installed up in an island off the coast of Finland. That was a whole bunch of stories there, but we got the data and we proved that yes, a three-bladed vertical axis turbine works, but you'll notice we still have guy wires. And that center mast has to be higher and the turbine has to be smaller. That turbine on the left is 25 kilowatts. So now we realize that we need a cantilever turbine. And we got an engineering team. I'll introduce you to them in just a second. They created this turbine up here in Denmark, full-scale prototype. It had problems. They could not predict harmonic resonance because, like every other vertical axis turbine company, they did not have an accurate computer model that would predict it. And that led us to hiring David Malcolm out of retirement, and he helped with that turbine, helped get the data from it, helped model it, and with that computer model, we were able to make this Model 3.1 and install it in Texas, and voila, it worked, and just like the model predicted in harmonic resonance, and that allowed us, and loads, everything, and that allowed us to predict, make this final Model 4.0 turbine that we are bringing to the world. So one of the interesting things about this is, how do you know that a turbine passes through a technology readiness level? Well, the data, strain gauge data, very carefully measured, matches what the model predicted. And that led us to David and Dr. Ola Jala producing a paper that was published in the Physics Journal that validates the accuracy of our modeling. And with that accurate modeling now, we are the first to really have a solid, accurate model that allows us to make a final commercial vertical axis turbine. So that leads us to who's this team. So Bob passed away, regrettably. We brought on Dr. Ajala about almost 4 years ago. She came on board because she really wanted to mentor with Dr. Malcolm. They have roots up there in same universities up in Scotland that they went to. And Dr. Malcolm was happy to mentor a young, brilliant engineer. And together they really worked that model out for 3.1 and redesigned the turbine for Model 4.0. Antonio here on the left and Yonit over in Europe, they were the designers of Model 3.0. Mark Chang was over on that island in Finland doing the controls. Antonio is our young intern who we hired as an engineer. These people all have experience with almost all of our past models, and they are a great reason why we are successful. Now I realize, oh my God, I'm running out of time. So this is what these turbines look like. The Model 4.0, they come in pairs about 3 feet apart. This is called a Campbell diagram. This allowed us to predict harmonic resonance. It shows up at 26 RPM. We start rotating, producing energy at 30 RPMs. We skip through the 26 RPM, and now we operate safely. So we solved that problem. We solved the problem of fatigue life. Now and I'll tell you in a second of how, we have a very accurate understanding of fatigue life, and the fatigue life says that these turbines should last 70 plus years, which is a fantastic result. Key thing we found was we hired Dr. Ayapara to redo the aerodynamic modeling and see if we could do a better blade. And yes, we could. This is a larger blade, and this blade allows us not to have to epoxy a plate on like the flow wind solution was. And this is what we did on our Model 3.1. We epoxied a plate on this blade over here on the left. And we got a patent for this blade. And we broke through and we got a patent for this blade arm connection. Oh, I should show this one first. I got it in the wrong order. So if you put a hinge between the blade and the arm, now you solve these movement problems of millions of times a year. That pin in the hinge is designed to handle the movements that happen super strong. Every 20 years, you replace the pin and it keeps going. So that was the breakthrough in solving that blade arm connection. Then you had this problem of, oh, the mast is very expensive. This pipe mast on the left that almost all vertical axis turbines, if you look at them, the center mast is a pipe. Pipes are difficult to work with. They're expensive. They're to figure out how to weld them properly. You don't really want welds on a machine that revolves millions of times a year. But with Jeff Willis's help, he's one of those engineers I showed you up there, we came up with this hex mast design. Oh, now you're bolting everything to flat sides. Huge breakthroughs. It allows us to think about putting hinges between the blade and the mast to solve additional strength problems and increase the ability of this turbine to withstand hurricane-related forces. And that was a critical invention. It also was a major money saver as well. So here, now I'm going to go into competition. I got about 10 minutes left. So our turbines, they can be on towers. The center of the rotor can be anywhere from 11 meters above the ground to 20 meters. 20 meters is roughly 65 feet above the ground, and that's in the center of the rotor. The blades are around 41 feet long, so that puts the top of our turbine around 86 feet high when it's got the center of the rotor is at 66 feet above the ground. We have aluminum blades. We're going to find out that we're the only ones with aluminum blades, extruded aluminum. We are at technology readiness level 8. We are ready for certification, and we have the aeroelastic model that validates it, and that's going through certification itself right now, which is great. I can tell you about that in some updates. So here is a interesting vertical axis turbine. They are struggling with this one. You'll see a number of these verticals that say, oh, these arms create drag. So if we can only use one arm per blade, we will reduce the drag and increase the efficiency of the turbine. But the forces on those blades are so much. And the higher the blade, the wind at the top of the blade is always higher than the wind at the bottom of the blade. And now gusts come through. So these type of machines have significant problems. You really need at least 2 connection points per blade. So we don't have much hope that this turbine will ever reach commercialization. X-Flow is probably the most advanced of the vertical axis turbines. It comes out of Dr. John DeBerry's work, and he set up a company with a brilliant guy named Dr. Ian Brownstein, who is the lead on this. If any turbine is going to have a breakthrough into the vertical axis turbine world, this is going to be it. I haven't found out what they're doing about this problem of blade arm connections. They don't have a patent for a hinge like we do. And so without that, I'm afraid that they are going to have to move their turbine up into laminar flow and keep it out of the wind near the ground. And so I haven't seen them saying that they're going to try to operate this in turbulent wind, but if anybody else can do it, I think Ian and Dr. DeBerry's team can. They are a few years behind us, but they are probably the biggest potential competition that Wind Harvest has. This is a fair wind turbine. Oh, look, it looks a lot like our turbine. That's because, like the horizontal axis turbines, vertical turbines are converging on the same thing. 3 blades, the same blade shape, the same arms that come out at angles, not straight out horizontal. And as you notice, this pipe is a pipe. It doesn't have a hexagonal mast. They are no longer, we haven't heard from them since 2022. We don't think they're in operation. We don't think they've ever made any sales. But I thought, oh, look, this is a convergence of vertical axis turbines. We're kind of all moving into the same direction. That's driven by aerodynamics and a couple other things. This is probably the most interesting new turbine coming out of Australia. It's a 6 kilowatt phase. I haven't heard anything about it in the last couple of years. It's going to, in theory, have a tremendously high efficiency, but it has the two blade problem that may be solved because the blades, you can see the blade spins all the way around, but it's a composite blade. Oh, composite blades are difficult to make, transport, build, install. They don't have patents for hinges on their blade arm connections. I don't know they're going to have to solve that problem without the hinges, but it is a super efficient shape. We are not going to go to this shape because we like our very straight, simple design of extruded aluminum blades and a very long life, and we do not want to have to work with composites if we don't have to. Now, this is the one that got the most airplay recently. It's called the Heirloom. When Bill Gates put $4 million into the Heirloom turbine, everybody thought, well, here we go. We got a new invention promising to be 4 times cheaper than any wind turbine on the market. It's a sale, but gosh, it's got problems. Paul Geip's got an article on this. If you look up Paul Geip Heirloom, you will see his devastating review of the problems of this. Mainly, turbulence. You're near the ground. How are you going to handle turbulent wind, gusts, and all the rest of the stuff? So I've heard that they've gone to 2 cables per blade. That makes sense. 2 arms per vertical axis turbine, 2 cables to this blade. That should help. Of course, the second cable creates drag and cost as it now moves around this track. So they are doing a pilot project with Bill Gates' $4 million. We are interested in seeing how that works. We suspect they're going to have to raise this up or find places where the wind is laminar. And that is not wind farms like the ones in California where the wind is highly, highly turbulent. So we don't have much hope that this Heirloom will be ever commercialized. But, you know, if it is commercialized and it's up there at 30 meters above the ground as the center of its kind of track, and the blades are 10 meters long, oh, we can put our turbines around and under them. And then the horizontals could be above it. So there could be a 3-layer solution, grabbing the super turbulent wind near the ground, like with our turbines, having this kind of device between above ours, but below the blades of the horizontals, and then above that, the horizontal axis turbines. So if they are able to actually solve this challenge of turbulence and a sail device, that they certainly could have a role in it, but we are pretty confident they will not be down in turbulent winds and they will not be in hurricane areas. This would have a difficult time in a hurricane like our turbines can solve. And that is the end of the deck. I want to remind you a couple people, the crowdfunding campaign is the way we raise the capital to bring these turbines, our 2 turbines, through certification. We have to certify a pair of turbines, not a single turbine, because 2 turbines is the minimum size order we're going to sell. When these turbines are placed a meter, 3 feet apart from each other, they increase the energy output of the neighboring turbine because they deflect wind into the neighboring turbine, and the wind speeds up through that gap. And when you have more speed on a blade of an airplane or a wind turbine, you get more lift, more torque, more energy output. So that is the cost of that is around $700,000 to install these 2 turbines, another couple $100,000 to get them through certification. And then that if we are on track, we will see these installed, our turbines installed next summer. And we may have some very good news about that in a week or two. And with that, my half hour is up. So I'm encouraging you to tell people about this investment opportunity. It's a very unique one. There is the first company that's made it into the turbulent wind space with a turbine fully ready for certification. And it is a unique opportunity to get into a investment before it becomes fully commercialized, and the valuation of fully commercialized products are always higher than they are before they're certified and sales start. So I look forward to hoping to have you as investors, and thank you so much for this time. Bye-bye.